Coming to the question, here is the problem statement. So you're going to analyze a continuous beam as shown in the figure by using a slope deflection method, and the support B and C sink by 10 mm and 5 mm respectively, and the support D rotates through an anti-clockwise angle of 0.1 radian. And here there are no loads on the beam. You're going to assume EI is equal to 8 into 10 cube kilonewton meter square. So for this is a given beam and there is no loading at all, and EI is equal to constant has been given. Each span of the beam is 5 meters, AB 5 meters, BC 5 meters, and CD 5 meters. So here in this question, it is given that B has been settled down to 10 mm to the B dash position, and C has been settled down to 5 mm, and the new position of the C is C dash, whereas the D has been rotated anti-clockwise direction of 0.1 radian. Okay, there are no loads at all. So this is a given problem statement. Now you're going to solve step by step. Coming to the step 1, you're going to determine the degree of freedom. So coming to this problem, so considering A support, here you are not having, you are having a rotation. So that means theta A is not equal to 0, whereas the displacement is 0. Therefore, delta A is equal to 0. And coming to this B point, here rotation is not equal to 0, whereas the displacement is given as 10 mm at B. Similarly, at the C, there is a rotation. That means theta C not equal to 0, whereas delta C is equal to 5 mm has been given. So that means B has been settled to 10 mm and C has been settled to 5 mm. Coming to the D support, it is having a rotation of 0.1 radian, which is of anti-clockwise direction, and delta D is given as delta D is equal to 0 since it is a fixed support. So EI is equal to constant for the entire beam. Now the degree of freedom is 3. So that is theta A, theta B, and theta C. So these are the 3 unknowns we are going to find in this problem. So this is the first step. Now coming to your second step. So here you are going to calculate the fixed end moments. So for calculating the fixed end moments, so here in this problem, the load is not given. Therefore, the fixed end moments for all the spans will be equal to 0. Here, as there is no external loading, so MFAB, MFBA, MFBC, MFCB, MFCD, and MFDC. So all the moments are equal to 0. And coming to the third step, here you are going to use the slope deflection equations. So now this is a given beam. Slope deflection equation is MAB is equal to MFAB plus 2EI by L into 2 theta A plus theta B minus 3 delta by L. So here in this problem, what is given actually, we will just see. So as this is a AB beam, one second. So as this is a AB beam, so this has been settled to 10 mm. So that is B dash. So here the settlement is a positive settlement. So here directly we can consider the delta will be equal to 10 mm. So that means delta will be equal to 10 by 1000 meters you can consider. So by substituting for AB span and BA span, that 10 mm to be in the positive value only. So you are going to get this equation. And similarly, for MBA also, same you are going to substitute. So that means you are getting the simplified equation to be in this way. So here, as EI is constant throughout the beam, so EI will be EI only. So span for AB is 5 meters. So the span L is substituted as 5 meters. And whereas theta A and theta B are not equal to 0. So those are the unknowns that have been given. Whereas here delta is equal to 10 mm. Therefore, as it is a positive settlement, so that delta will be considered as 10 by 1000 meters. So that will be substituted here. 10 by 1000 into 5. So this entire thing, you're going to get it in a simplified format. So similarly, MBA also. And in the next step, you're going to do for the other span, that is your BC span and CB span. So now coming to your BC span and CB span, I'll just draw. So this is your BC. So this is BC. So here you are having a 10 mm settlement and here you are having a 5 mm settlement. So this is 10 mm and here this is 5 mm. So that means together when we see the net displacement, so the net displacement will be equal to 10 minus 5. So that is 5 mm. So that means B is shifting to B dash, whereas C is shifting to C dash. So both 5 mm will be common. So the extra displacement, that extra settlement that is taken over at B is 5 mm. So therefore, here you are going to substitute delta will be equal to minus 5 by 1000 meters in both the BC as well as for the CD. Why? Because here you are having the negative settlement as for the BC. So your extra of 5 settlement is there. So that 5 mm settlement is nothing but 10 minus 5. So that will be equal to 5 mm. So when we substitute here, so here we are substituting that delta will be equal to 5 by 1000. So that is positive only. So why? Because it is positive, minus of minus, it is going to become a positive value. Similarly, MCB also, you are going to substitute all the values. So here also delta will be equal to minus of minus 5 by 1000 only. And EI is constant throughout and where the fixed end moments are 0 for both the cases. So this is related to the BC span and CD span. Clear? Now coming to your next step. So that is related to the CD span. So now coming to this CD span. So this is your CD. So now this has been a settlement of 5 mm. So delta will be equal to, which is of negative value. So this will be substituted by 5 by 1000 meters. So both in CD as well as in the DC cases. So now why substituting this minus of minus? So this will become plus. So delta you are going to substitute by 5 by 1000. Okay, so here the span is 5 meters. So it is 5000. And one more thing is here you are having a rotation. So rotation which is of anti-clockwise direction of 0.1 radian. So that means here you are going to substitute theta d will be equal to 0.1 radian. So that will be negative sign. So this is theta d is minus 0.1 and this delta will be equal to minus 5 by 1000. So span is 5 meters. So you are going to substitute in this equation. Similarly, MDC also will be equal to MFDC plus 2EI by L into 2 theta d plus theta c minus 3 delta by L. So here also you are going to substitute in the place of theta d minus 0.1 and in place of delta you are going to substitute plus 5 by 1000. So by simplifying this entire equation you are going to get this. So these are the final end moments by substituting all the unknowns and known values. So now coming to your next step, so that is your equilibrium equation. So coming to your equilibrium equations, so here you are having MAB. So moment at the hinge support will be equal to 0. So that means moment about AB will be equal to 0. Next, joint equilibrium conditions. So that is sigma MB will be equal to 0. And whereas the moment about C portion will be equal to 0. So that is another joint equilibrium condition. Whereas for the fixed support, there will be a moment. So here you are having three unknowns and you are having three equations. So what are the unknowns here? Theta A is your unknown, theta B is your unknown, and whereas theta C is your unknown. So now substituting in these equations, that is sigma MAB equal to 0. So this is an equation. So by simplifying this equation, this is the first equation. And coming to next one, that is sigma MB equal to 0. So that means BA moment plus BC moment will be equal to 0. So by substituting these two, you are going to get this second equation. Now coming to the third point, that is sigma MC will be equal to 0. So coming to MC equal to 0, that is moment in CD, and CD will be equal to 0. So by substituting these equations, you are going to get the equation 3. So now we are going to solve this all three equations and going to determine theta A, theta B and theta C. So in the next step, you are going to solve the 1, 2 and 3 equations. So by solving these three equations, we are getting theta A will be equal to some 0.006615. So that is a positive. So that means you are getting a clockwise rotation. And similarly, theta B we are getting in a negative value. So that means it is in anti-clockwise direction. And whereas theta C you are getting a positive value. So that means again it is a clockwise rotation. So these are the three unknowns that we have been solved by using the three equations. So after getting these values, we are going to plot a elastic curve. So to draw the elastic curve, so these are the values. So for these values, we are going to draw the elastic curve. So just see. So this is A support. And this is B support. And this is C support. And this is D support. So here theta A, you are having a clockwise rotation. So that means your curve will be okay like this. So when we draw a tangent, when we draw a tangent to this line, so you are getting a clockwise rotation of theta A will be equal to 0.006615 radian. And similarly, when we draw a tangent to this B point, you are getting an anti-clockwise rotation of theta B will be equal to 0.007230. Again at theta C, when we draw a tangent, so when we draw a tangent, so this is again in the clockwise direction of theta C will be equal to 0.025307. Whereas at the theta D, it will be 0. Why? Because it is a fixed support. So this is so this theta C is equal to clockwise. So this theta B is anti-clockwise direction. Again, this theta A is equal to clockwise direction. Okay. So this is how you're going to represent your elastic curve. So by drawing a tangent to this curve and to this tangent, when we draw a rotation, so that should be in the clockwise. So that will be positive. If it is in anti-clockwise direction, so that will be equal to negative. This is how you are going to represent your elastic curve. So after getting your theta A, theta B, theta C, then you are going to substitute these values in final end moment equations, that is lower slope deflection equations. You are going to get your moments. So this is your MAB moment, and next is your MBA moment, and then MBC moment, and then MCB moment, then MCD moment, and MDC moment. So these all moments are in the Newton mm. And first one, anyway, you're getting a zero value. So that will be a zero. Why? Because it is a hinge support. So after getting this moments, we are going to draw the bending moment diagram. So these are the final end moment values. So first we'll draw a free body diagram. Then we'll draw the bending moment diagram. So first we'll draw a free body diagram. AB, BC, and CD. So for AB, so first we'll note these points B, C, and D. So AB, so this moment is 0. And for BA, you're having a anti-clockwise negative value. So that means it should be in anti-clockwise direction. And again, BC, you're having a positive value. So that means again, it is in the clockwise direction. So both are 44.43 kilonewton meter. And again, CB, you're having positive value. That means clockwise direction. Again, CD, you're having, CD, you're having negative value. So that means anti-clockwise direction. So which is of 148.4 kilonewton meter. And whereas coming to DC, you're having an anti-clockwise direction. So that is negative value. So that is 549.4 kilonewton meter. So here you can see AB moment is 0. BA moment is negative. So it is in anti-clockwise direction. BC moment is positive. So that means it is in clockwise direction. And again, CB moment is positive. That means clockwise direction. CD moment is negative. That means anti-clockwise direction. Again, DC moment is negative. So that means it is again a anti-clockwise direction. So now coming to drawing a bending moment diagram. So for this will be equal to 0. And whereas coming over here, it is a sagging moment both sides. That means positive value. So it is 44. And again, at this point, it is having a hogging moment. So that means again, it is negative 148.4 kilonewton meter. And here it is 44.43 kilonewton meter. Again, here also it is having a sagging moment of 549. So somewhere here, 549.4 kilonewton meter. So this is not up to the scale. So here we can just see, just I'll draw the figure. Just a minute, I'll just draw the figure. Okay. So this is a positive value of 44.43 kilonewton meter. Why? Because at this junction, you are having a sagging moment. Again, at this junction, you are having a hogging moment of 148.4 kilonewton meter. Again, at this junction means this point is C and this point is B and this point is A. This moment is 0. Whereas at this position, it is D, which is of again sagging in nature. So that is 549.4 kilonewton meter. So this is your result. This is your bending moment. So here as there is no external load, so we are not combining both final fixed end moments and simple bending moment. Okay, here there is only the final end moment. So there is no external loading. So due to this external loading, we are not having any moment. So this is a final bending moment diagram. So one more thing is just a sign convention. I'll just draw it here. So sign convention for your bending moment diagram. So sagging nature, sagging moment is always a positive moment. So when two arrows are upward, so this is a sagging moment. And whereas coming to the hogging moment, so this will be negative when both arrows are towards. So that means this is a hogging. So here you can say this is a sagging moment. And here you can say this is a hogging moment. Again, this is a sagging moment. So that is how we represented the bending moment diagram. So that's all. These are the references. And thank you.